Okay, let's discuss another example. So I'm referring the exercise number 4 in your slides. So we have a kind of a periodic signal. So if I draw it, it's something like this. So we have a periodic signal. So it's a kind of a square wave type. So once we mathematically model this function, we can simply say like that. So we have xt. This is our time varying function, which is our periodic function. It has two values. One is 1, and t is in between t1 and minus t1. This is minus. So 0, otherwise. Or else we can say like 0 for two regions, t1 to t by 2 and minus t1 to minus t by 2. Okay, so we can rewrite this using the mod operation. So we can rewrite this using this mod t is less than or equals to t1, and here you can simply say that t1 mod t t. So both represent the same data. So this is the function which we are referring here. So it's a kind of a periodic function. So at the period, so the period is actually t. But this particular function is not defined through the entire period. This function is non-zero. This function is non-zero between this region minus t1 to plus t1 during this. So this is the period of the function, and this is non-zero during this period. Okay, so we are asked to write the Fourier series expression. We need to write the Fourier series expression. So how do we do that? So for this kind of examples, we need to go for the basic definition. So the definition is actually, if we have a periodic function, we need to represent it using an infinite sum ak e to the power j k omega naught t. So we can simply say that here t, which is the period, equals to 2 pi over omega naught. So from that we can replace any omega naught using 2 phi divided by t. Okay, so AK can be derived like this: 1 over t integration of the period, then xt e to the power minus j k omega naught t dt. And this is the way of evaluating this Fourier series coefficients for any given k. So this is the definition of the series expression or the series expansion of this periodic function xt using a complex exponentials. So these AKs are Fourier series coefficients, or the coefficients representing the impact or the contribution to the expression. So from this we can derive these individual coefficients. Let's see. For this particular case, we have a special value which is our DC component A naught. We can easily get A naught by integrating the period xt dt. So k equals 0 means this exponential converges to 1. So ultimately we'll end up with the simple average. So this is the simple average. This is simple average. So we can find the DC value A naught. A naught equals 1 over t. This is our period. So we need to perform an integral over a period. So the period is actually, for this case, it's like minus t by 2 to plus t by 2. So this is actually, if we consider the entire period, this is minus t by 2 to plus t by 2 xt dt. So, but this particular function is defined only between t1 and minus t1. So our integral simplifies to this range xt dt. So once we substitute the value for xt is actually 1 during this region. So then it becomes 1 over t minus t1 plus t1. The value of xt is 1 dt. So if we solve this, you will get this 2t1 divided by t. So this is the Fourier series coefficient at k equals 0, or the DC component of this Fourier series expansion. So then we'll move to next how to find the other set of AK values. So then for AKs, we can simply say that this is again minus t by 2 to plus t by 2 xt e to the power minus j k omega naught t dt, where k not equals to 0. So once we substitute this or simplify this, we can simply say that we can simplify the integral to this, and xt is actually 1 e to the power minus j k omega naught t dt. Once you solve it, once you integrate it and substitute, so you will end up with this kind. Like for example, how do you integrate it? So this is a exponential function, we can simply put like this: e to the power minus j k omega naught t divided by, this is integrate with respect to t, so that we can treat this j k omega naught as a constant. So this is j k omega naught as a constant, and the limits are like minus t to plus t. Okay. So then once you substitute this, so we have this kind of expression: e to the power j k omega naught t1 minus e to the power minus j k omega naught t1 divided by j k omega naught. Okay. So then we know that omega naught is equals to 2 pi over t. So we'll substitute these two to here. So then we have this e to the power j k omega naught is actually 2 pi over t into t1 e to the power minus j k 2 pi over t into t1 divided by j k 2 pi over t. So let's say like, so we can replace this e to the power functions using sign. So we'll put like this. We'll do kind of, we'll put 2 here and put this e to the power j k 2 5 t1 of t minus e to the power j k 2 5 t1 of t divided by 2j. So this 2 to this 2 is cancelled. So then we have another quantity. We don't need to do this. Anyway. Yeah. So then we have k here. So we can simply represent this compound as sine 2 pi k t1 over t. Here we have t k 2 pi. Again, so then this can be simplified to this form: 2 sine, so k is k 2 phi t1 of t 2 phi k. So if we further simplify, this is like t over phi k sine 2 phi k t1 of t. So these are the ak values actually. For k not equals to 0. So now we can simply represent this xt, which is equals to 2t1 over t plus sum of k goes from minus infinity to plus infinity t over phi k sine 2 phi k t1 over t e to the power j k omega naught. You can simply say that this here k not t equals to 0. So this is the Fourier series expansion for the given periodic square wave type function. Okay. So if we want to further simplify this, we can do kind of a simple mathematical manipulation using. So we are planning to replace this expression using sinc function. So the sinc function sinc x actually equals to sine x divided by x when x not equals to 0. If it is x equals 0, then the sinc x equals 1. Sinc x equals 1 when x equals 0. So we can use this one. So previously we had a kind of expression like t over phi k sine 2 phi k t1 over t. Okay. So we can simply replace, we can have this, so we can rearrange these terms. So we have this sine 2 phi k t1 over t. So this is your x. So you can put x here. So we need to put 2 phi k t1 over t. So this t is here, phi k also here, but the only missing component is this 2t1. So we can put 2t1 here, and then we can replace the sine 2 phi k t1 over t divided by 2 phi k t1 over t using a sinc function. This is sinc 2 phi k t1 over t. Now we can rewrite this Fourier series coefficients. So this is 2t1 over t for k equals 0. So this is 2t1 sinc 2 phi k t1 over t for k not equals 0. So this is your Fourier series coefficient. Okay. So then if we can, so we can further simplify this if we have a kind of exact idea about the t1 and t. For example, as in the example, we use this condition. We have a period t equals to 4 times t1. So then we can simply say that a naught equals to, so this is t is for t1, so a naught simply equals to half. What about ak? 2 t1, so t1 is actually t divided by 4, and the sink, so we have 2 5k, t1 is actually t divided by 4, so we have, this is here we have t divided by 4 divided by 4 sine k5 over 2. I think I made a small mistake that t should go not be there. So for example, let's assume the t should be there. So it's like, it's not approximation, sorry. This is equals to half sin k5 over 2. Okay, not equals to. So we have a naught which is equals to half, and rest of the coefficients AKs are actually equals to half sin k5 over 2. So this is the sinc function. So we know that sinc function is something like that. This is symmetric. And these crossing points are basically when the argument inside this bracket goes to 0. So these crossing points are simply occurs when this argument k5 over 2 goes to 0. So then we can simply say that what are the k values this particular argument goes to 0, because we know that sinc function is a function which is directly related to sine. So then if the sine x component goes to 0, then sinc x would be simply 0. So then sine x is 0 at, like, for example, 4 different set of k values. So we know that, so this particular component is 0 at when k equals a kind of like 2, 4, 6, 8, similarly plus or minus. So then we know that. So now we have AK, which is equals to half 4k equals 0, and half sinc, so, k5 over 2 at k not equal to 0. So if we expand this one, we know that for odd values of k, we can simply evaluate the sinc k phi over 2. But for even values of k, so once it's even like 2, so we have sin phi. Sin phi means sin phi over phi. Sin phi is actually 0. What about 2 phi? So then like k goes to 4, then we have sin 2 phi, again 0. So this is 0. So then we can, if you want to represent this xt again using Fourier series, for t equals 41 scenario, this is actually half, and sigma k equals minus infinity to plus infinity. K only includes two odd, and k not equals to 0 case, we have this. So this is the representation. Okay. So how do we plot this for magnitude and phase? So this is the values of a case. So how do you do it? So this is a real number. These are two real numbers. So we can simply say that, so if you want to plot the magnitudes, so at k equals 0, we have half, and for the rest of the k values, is simply following the sinc function. This is simply following the sinc function. So we know that this is simply happens at k equals 2, this is k equals 4, this is k equals minus 2, this is k equals minus 4. So we know that we have one sample for the one value ak at k equals 0, and this is 0, this is 0, this is 0, this is 0. So then so the for the odd values of k, so the magnitude of this ak is simply the value of half sin k phi over 2. So which means for k equals 1, so we have this, k equals 3, we have this, k equals 5, we have this, minus 1, this, minus 3, like this. This is k equals plus 1, plus 3, plus 5, minus 1, minus 3, likewise. So this is the magnitude of AK. See, so the magnitudes are discrete. So we have these stems at each and every k. So for odd values of k, we have 0 coefficients, and even values of k, we have 0 coefficients like here, and odd values of k, we have magnitudes which are simply aligned with the half sin k phi over 2. So this is the magnitude spectrum of the function xt, which is a kind of a periodic function having this square wave, square. So there is a kind of a periodic function in a square wave manner. So I believe like this example clarifies how we can use special functions to get a kind of a simplification for certain xt's which we need to get the Fourier series. So once we apply Fourier series through this basic definition, so we need to get this integration involved, and you should be be careful of handling these integrations. So at the end of the day, you can replace these coefficients using different special function which we um, discuss in this particular module.